Welcome to Brain Vision.
So we have a train and a car, and I think the wording of this question is a bit confusing, but if you just look at the diagram, it's a little more straightforward. So there's a car traveling at 95 kilometers per hour, and it overtakes a train, and by that it just means it passes the back part of the train, which is also going in the same direction at 75 kilometers per hour. So this is the train and the car. And we want to know, once the car gets to here, of course the train is also moving, but once it gets to the front part of the train, how far has the car traveled? And then flip it around so it's going the other direction, and then we'll find that answer as well. So if we want to know when the car is going to pass the end of the train, then we know that the car is going to travel 1.1 kilometers past or farther than the train has traveled. The train is 1.1 kilometers long. So we can say for the car, our displacement, our horizontal displacement, is just vt, because there's no acceleration, so it's just velocity times time. And then for the train, we want the delta x to be, again, vt, but then we're going to add on 1.1 kilometers because the car is going to go 1.1 kilometers more than the train. And we know the velocity for both. We know for the car it's 95, and I'm just going to keep it in kilometers per hour. You could convert it to SI units, but everything is already in kilometers, so I figured just keeping it that way makes it easier. And the delta x for the train is 75t plus 1.1. And now we know that we can set the two displacements equal to each other. So 95t equals 75t plus 1.1. And just combine the time terms and we get 20t equals 1.1. So t is equal to 0.055, and this is hours because we're in kilometers per hour. And so now we can plug this back in to our initial displacement for the car. And we know the velocity is 95, the time it takes to reach the tip of the train is 0.055 hours, and that gives us a displacement of about 5.2 kilometers. So that's the first part. And now we want to know what happens when they're going in opposite directions. So I'm just going to say the train is now going this way. And to figure out what we want for the equation this time, the car is still going to be the same. We'll say 95t. But this time the train, so however far the car goes, let's say it makes it here before it passes the train is going to go this distance, which is 1.1 minus however far the car went. So we can say that the car has gone 1.1 minus how far the train has gone. And then just set these two equations equal. So we have 95t equals 1.1 minus 75t. And now combine the t's again. Now we have 170t equals 1.1. And for this, our t is about 0.00647. It keeps going on. And again, plug back into this. And so we get delta x for the car is 95 kilometers an hour times 0.00647 hours. I don't know how long that is off the top of my head, but we don't need to know the time, we just need the distance. So when you multiply those out, you get about 0.61 kilometers. And these answers seem to make sense because when they're going the same direction, it's going to take a lot longer for the car to catch up than when they're going opposite directions. And that's reflected in our answers.